Hi. So in part one of this Fourier transform series, where I talk about coding the FFT in MATLAB, we discussed the idea of a two-sided spectrum. And I'm summarizing this here. I recommend go checking out that other video to gain some insight into this problem. But essentially, we were given some function x of t that I told you was 6 sine of 4 pi t. In this situation, omega is 4 pi. And if omega is 4 pi, that means that our frequency in hertz has to be 2 hertz. That is what our signal is for this specific data set. I also tell you that we sampled this signal at 40 samples per second, and we did this experiment for a total of 2 seconds. We recorded that signal for a total of 2 seconds. Now, if we went ahead and plotted this, we would get a magnitude graph that looks something like this. In MATLAB, we know from the FFT that we will end up with amplitudes at both positive and negative frequencies. This is a consequence of the fast Fourier transform. And we'll see that we'll have frequencies at positive 2, because again, our frequency is 2. And we'll also have the corresponding negative signal of that frequency. So we'll have some amplitude at positive 2 and negative 2. Each of those amplitudes are half of the amplitude of the original sine wave. Basically, this 6 is split between the positive and the negative frequencies. So we see amplitudes of 3 at each of these locations. And I know it might look confusing. Why do I have this written as negative 2 when it's, in the positive x-axis direction? In MATLAB, they don't store it like you typically would. By default, what happens is that we store the negative frequencies on the opposite side of the Nyquist frequency, because usually there is no content here. Because if there is frequency content above the Nyquist, it would be alias down. So that means that we basically have this storage space to put other types of information. And MATLAB has decided to use that storage space for negative frequencies. Now, the meaning of this is that this is negative 2, but we'll see that when you plot it, it won't show up as negative 2. It's still a positive x-axis direction. It'll be symmetric about whatever the Nyquist frequency is. And for this example, I told you the sampling frequency was 40. That means that this Nyquist frequency is 20. So therefore, this distance here is 18. And this distance here is 18, which means this negative 2 will actually show up as positive 38 hertz. But that is just showing us the content associated with the negative frequency. Now, that's not necessarily useful to us. I mean, a lot of times we're interested in what is the amplitude of the sine wave. We don't really care about, its negative counterpart. That's just a consequence of the math. So what we would rather do is take this two-sided spectrum, and again, two sides means you have positive and negative frequencies. We want to convert that to a one-sided spectrum. And that's the objective of this video, just to understand how to do that properly. And if we look back in time, I included some code here that we discussed in part one of this video series, where I take my signal X, I find the FFT of it. This will give me a complex signal in many cases. And what I would do then is take the magnitude of it, that complex numbers, by using the ABS function in MATLAB. And then I have to normalize by the total number of samples. That is a consequence of using the FFT algorithm. We have to normalize by the total number of samples in our data set. The other thing that's important is, now that we found the y-axis values, essentially this 3 and this 3 at these two locations, we need to figure out where they correspond to on the x-axis. So we find our frequency resolution, which is 1 over the total time of that acquisition. We discussed in the last video why that's true. And then we'll plot from 0 hertz up to the sampling frequency, but minus the frequency resolution. We expect to have 40 data points for our frequency because in this situation, sorry, not 40, 80. We expect 80 points because of the fact that our sampling frequency was 40 samples per second and our total time was 2 seconds. So we expect 80 samples. That means that this ends up being 80 samples. This is 80 samples. This also must be 80 samples. If I start at 0, then that means that I have included an extra one there. So if I'm going up from 0 in increments of df, which in this case is a half, I cannot go all the way up to 40 hertz for my sampling frequency. I have to do 1 frequency resolution less. That'll basically make sure that that frequency vector is 80 samples and we can plot it. And if we plotted it, we would end up with something like this. Now for the one-sided spectrum, what that means is we want to take our negative frequency and account for it without including that in our plot. So essentially what we would rather do is that instead of plotting to Fs, we plot, when I say Fs, I'll be really specific. Instead of plotting to that final frequency, Fs minus df, we'll plot to the Nyquist. So essentially now, instead of showing this plot that is two-sided, where we see that we have content on both sides of the Nyquist, basically we will not have any content over here anymore. It'll be on the left. And in doing so, we have to change our frequency vector, and we have to change the magnitudes. Because what we're going to do is we're going to take this peak here, because again, -2 hertz is not a physical thing. It's more so a mathematical consequence. I want to take this, I would like to take this, and I want to put it right on top of the 2 hertz to account for that power. And if we do that, we end up with the correct amplitude of 6. So if we have to do that in code, so how do we do that? First off, what I would like to do is I'm going to say that my X mag, which we already found up here, this is already normalized to the correct amplitudes. What I would like to do is 2 things. One, I want to make sure that I am only including frequencies up until the Nyquist, and I need to double those frequencies. So I'm going to say that X mag is equal to X mag and there's an easier way to do this, I think, that would make sure that this is more foolproof. I want to figure out what indices I need to take. And remember, for this problem, this X mag is originally 1/80, where this 1 corresponds to the magnitude at 0 hertz, and this 80 is the magnitude at Fs minus df. So what I would like to do is set it up in such a way that I will just get the magnitudes from 0 to Fn. And if I'm including Fn, and I'm also including 0, that means that my new plot will not be a vector of 80 elements, and it won't be a vector of 40 either. It'll be a vector of 41 elements, considering the fact that I am including both Fn and this extra frequency at 0. And not everybody includes this extra Fn. I just am for completeness, I guess. But what I would like to do is say, okay, let's go and take the elements from 1 to 41. And essentially what we will do is take the length of that vector and divide it by 2. That will give us 40. But if I'm including the Nyquist frequency, I'll go ahead and add a 1 to it. So now this length here is 1 to 41. We don't need to normalize again. We've already normalized. But what I do need to do is if I am getting rid of and ignoring those negative frequencies, I have to double the amplitudes in that vector. So I'll say x mag maybe 2, or maybe I'll say 1 for one-sided. This will be that x mag we found originally times 2. I have doubled all the frequency content. Now there's a little caveat here. If we think about the idea that if I have a signal that is split between positive and negative frequencies, we see that that amplitude is divided in half. Because if I'm at positive 2, there is a frequency peak at negative 2. If I am at positive 1, there's one at negative 1. If I'm at positive 3, there's one at negative 3. What about 0? Let's say I have a DC signal or a mean signal. Does this have a negative counterpart? Is there a positive 0 and a negative 0? No. So when we do the original two-sided spectrum, we will see that if we have any content at 0 hertz, and again, 0 hertz means a static signal, or a mean, or a DC offset, there's a bunch of different words for it, that power is not split. And right now, we just doubled that power. So we have to undo that doubling at 0 hertz. Excuse me. So I'm going to say that x mag 1, the first element there, because the first element, this corresponds with 0. That will be equal to the first element that's been doubled. We are undoing the doubling. And now we're good, essentially. We have set it up so that we have doubled all the content except at 0 hertz. We have to undo the doubling that we accomplish here to make sure that we're not including extra content at 0 hertz, because that power is not split. We just be pretending that it's bigger than it actually is in that situation. So this is our y-axis. If we go ahead and do our x-axis now, let's say f plot for a one-sided spectrum. This will start at 0. We'll go in increments of df. And in this problem, I told you we're going to add the Nyquist frequency. So I'll just do fs over 2. And then we plot. And now we have our one-sided spectrum. So what I would like to do is show you this quickly in MATLAB. Let me come over here and stop sharing there. And let's come to my MATLAB. Come to my MATLAB. This is the spectrum that was two-sided originally. We see we had at 2 hertz and at 38, that's corresponding to the negative 2. And here's the code for that. For again, in this case, I defined the x-axis vector. I found the FFT and normalized it by the number of samples. And then I plotted it from 0 to fs minus the frequency resolution. And I've also included that Nyquist frequency so we can see that it's symmetric. Oops, it didn't plot there. Now we can see it. There's our Nyquist frequency at 20. So let's go ahead and do what we just said. Let's convert to a one-sided spectrum. I'm going to say that X mag, and I'll say 1 for one-sided. That's going to be the current X mag, and I'm only going to take the elements from 1 to the length of X mag divided by 2 plus 1. This includes 0 hertz and the Nyquist. I would also like to double that to ensure doubling for correct amplitude. So we account for the negative frequencies. And then I'm going to say that the first element in there, which is the 0 hertz one, we have to have that, having 0 hertz. Now in this problem, I didn't give you a 0 hertz signal. There was no DC offset or mean. But we want to get in the habit of doing this because in many cases you might. It depends on the situation. So let's compare. If we come up here, we see X mag. And all of it's 0, except for here we see it's 3. That's associated with 2 hertz. And we had a frequency resolution of a half. So 0, 0.5, 1, 1.5, 2 hertz. And then on the other side, we have the negative content that's also 3. Now, if we run this and we compare X mag 1 now, I guess I haven't taken the, no, that's fine, X mag 1. We will see now that we have 41 elements that goes up to the Nyquist. And now we see 0, 0.5, 1, 1.5. Now we have an amplitude of 6 at the 2 hertz location, which is what we want. We want that peak to be matching the amplitude of the original sine wave. Our F plot is going to go from 0 in increments of df to the Nyquist frequency. And I'll go ahead and now I'll plot it. And maybe I'll do this on the same graph so we can see it. We'll run this section. If we come here, you'll see now that our red graph goes up to 6 at the same location because we're including this 38 hertz peak, the -2 hertz frequency, on top of this one. And everything that's over here, everything that's over there to the right of the Nyquist frequency doesn't exist for this new vector. You can see here that when I plot it, that it doesn't even go past 20 because there's no content there. So that's the idea of a one-sided spectrum. An easier way of doing this, I think, is instead of dealing with this, because this gets a little bit complicated, let's go ahead and define our F-plot1 first. And what I'll do is go from 1 to the length of F-plot1. That's probably a lot easier, considering that the length of F-plot1 is 41. So now we're going from 1 to 41 if you're going to include the Nyquist frequency. I'm hoping that this makes sense. If you have any questions, please let me know. And I think that's it. Okay, thanks for watching. Bye.